So thank you everybody for joining the OFA webinar this morning. It's the Flux Framework, Modern Hierarchical Resource Management for Managing HPC Workloads, presented by Nate Hanford and William Hobbs. So first, we did want to go over just a few quick housekeeping items. So for attendees, please remain on mute, but during the webinar, if you do have any questions for the presenters, please submit them to the host via the chat feature, and then we will get to them as time allows after the presentation. And as always, please be courteous and respectful. So now I will introduce our speakers. So we have Nate Hanford. He's a computer scientist in the Livermore Computing Division at the Lawrence Livermore National Laboratory. And then we also have William Hobbs, who's a software developer in the Livermore Computing Division, also at Lawrence Livermore National Laboratory. So Nate and Hobbs, welcome. Thank you so much for being here, and please take it away.
Great. Thank you, Liz, and thank you to Phil and Mike for agreeing to let us do this and suggesting that we should. Um, Today, we're going to talk about Flux and a little bit of history of resource management in HPC at Livermore National Lab, and hopefully get into a little bit more of the developer interfaces that Flux provides. And we'll talk a little through a simple container demo, and hopefully leave enough good bit of time for questions at the end for anyone who wants to pipe up and ask about different things in Flux. This may be to many of you who use HPC resources all the time, this is going to be very simple, but I know that we cast a wide net with a lot of kernel developers or fabric developers or developers of other services. So I just wanted to kind of set the stage that the resource manager, whether it's Slurm, whether it's Flux, whether it's LSF, is basically the user's only entry point into HPC resources. It's not always, it doesn't always look that way, because sometimes users are using things like a REST API that's built on top of a resource manager or a workflow manager. But resource managers provide all of the scheduling, the job launch, the actual resource specifications. So if I request 4 nodes, the resource manager decides what 4 nodes of the 1,000 in a cluster I get. The PMI service for MPI jobs. So, setting up the PMI server that allows MPI jobs to launch. Accounting and bank information. In our center, this looks like setting priorities. So determining how quickly a user can run on the system, and limits, so how many jobs at a time a user can run. And within the Flux framework, instead of doing all of these things in just one package, we split these responsibilities into multiple components. So we have an underlying set of core services that allow people to set up a network for messaging and create messages based on job specifications, and can launch jobs. But for more advanced graph-based and arbitrary resource scheduling, we have another component called the Fluxion Scheduler that adds on that ability. For multi-user instances, we have a very small set of setuid components that are kept in a separate repository. This also allows us to more closely scrutinize anything that's running with elevated privilege. We have a separate project for accounting. So for user limits for bank and accounting information, that's all kept in Flux Accounting. And for the specific PMI services that are required to support OpenMPI version 5 and above, we keep those in a separate project called Flux PMIX. And this may seem like, I don't know, this may seem like a lot of different packages that you need to run a resource manager, but one of the things that this does is it separates concerns, and it means that you can do a lot of things without any elevated privilege at all. And I'll get into a little bit more of that in a minute. I won't dwell on history too much, except to say that at the lab, the laboratory system software group has been at resource management for a really long time. And I think that the issues, the lessons that we've learned, and sort of the issues that have come up in that time have led to a really robust design for Flux, and have enabled us to really be very thoughtful in our development approach on the Flux team. And I think that's because we have a long history of interacting with a lot of different users and a lot of different system administrators that have influenced that process. The most recent big interaction that we had was getting Flux on El Capitan, which Nate was heavily involved in. So I'll let him talk to some of the acceptance and system issues that came up there. Nate, you want to?
Yeah, so Flux is our system scheduler for our top supercomputer, El Capitan, along with several of our other machines that drive our modeling and simulation mission here at Lawrence Livermore Lab. We have also had these systems demonstrate significant promise in their capability of processing agentic AI workflows and large language models and other AI-related workloads as well. And the Flux scheduler gave us the ability to do a lot of that. The hierarchical nature allows us to do a lot of things that we couldn't do before, and that was one of the reasons we chose Flux, along with multi-constraint scheduling, which I'll get into on the next slide, having to do with why we went to Flux for LCAP. But we absolutely use this in production. And it is the system scheduler on El Capitan. We'll talk about some features of Flux later that allow you to run Flux alongside of the Slurm scheduler, but there is no Slurm on El Capitan. There is only Flux. It is the resource scheduler for that system, along with all the systems listed here. Take the next slide, please. So when we did acceptance for El Capitan, we really made sure that we battle tested Flux. We launched jobs that scaled to, whereas Flux had initially started on some of our smaller clusters of only a few hundred nodes, we scaled up to tens of thousands of nodes, and we were able to scale up to, about hundreds of thousands GPUs and over 1 million individual ranks or communicating processes. One of the main reasons we, as I previously alluded to, chose Flux for El Capitan is due to the capabilities for the plugins, the software flexibility, and the ability to do multi-constraint scheduling, which we needed to support not only advanced fabric features and Slingshot such as VNI, but also our features related to storage, including ephemeral and persistent Lustre file systems on what are called rabbit nodes, which are essentially heterogeneous compute and storage nodes that are deployed out in the fabric with direct PCI Express links within a rack to other compute nodes in the rack. This required serious engagement with system administrators here at Lawrence Livermore Lab, and also our vendor, Hewlett-Packard Enterprise, and a lot of their technicians and developers and partners to extend Flux and to engage in the Flux software ecosystem. This also gave us an incredible growth in user base, with users bringing us not only our traditional scale-out jobs, but a whole new category of workflows, which I guess would also be the third reason that third main reason we really chose Flux for El Capitan and our next generation architectures is because previously many users had actually a Flux requirement dependency even within clusters that had Slurm, because they needed to run hierarchical jobs with many different job steps or workload components per individual node. And that's one of the many things that Flux enables us to do.
So, as I said before, Flux builds on a lot of the LLNL expertise and resource management. And one of the things that the way that we do this is by separating concerns through allowing broker modules and plugins that allow specifically hardware specific, as Nate mentioned in the past slide for Coral 2, or scheduler specific code to remain out of the Flux core tree. So we separate concerns that way. This also means, again, that we can not only run completely in user space, but as Nate mentioned, prior to having Flux on LCAP, we had users that were running on Lassen or the Sierra class of clusters or our Slurm clusters, that we're starting Flux as a job. So Flux can start as a distributed application like an NPI distributed application under another resource manager. So it can be run under a container, it can be run under the resource manager, and it can run under itself. So the ability to run in user space really enables you to subdivide a lot of the core services that Flux provides almost infinitely. And I have a graphic for that in a minute. This is kind of a representation of the way that of what an overlay network might look like on an 8-node cluster. So there are many critical services that are at rank 0, kind of at the top. That's like the job manager, the scheduler. The job manager is the thing that's in the path of moving jobs between each of our states. So the Flux jobs represent a state machine that I'll explain more in depth later. And the scheduler, which is determining, where things should go. A lot of the modules, though, run on all ranks. So we have a key value store that's distributed across all of the ranks. You can put data in, take data out of the key value store yourself, or there are other, if a batch job by default will store its input and output in the key value store to a limit. So that's that's one of our modules that's distributed. We have a feasibility module that can be distributed. So you can run the feasibility module will just reject jobs that would never be able to be scheduled. You can run that across all of the login nodes in a cluster and have a quicker loop to getting users to kicking out jobs that aren't relevant. And all of this is enabled by modules sending and receiving messages over TCP/IP via 0 and Q sockets. So that's why the core set of services is really messaging in the KVS, and job launch and its modules that come with the core set of services are all built on top of that. We've mentioned the hierarchical nature of Flux, and this is a really cool graphic that my colleague Dan Milroy made that I'll use to explain this. If you imagine that these tiles are a cluster, and the entirety of the cluster is scheduled using a first match policy. So that means when the scheduler is able to match a user's request to a resource request's, take it. And an easy backfill queue policy. So this is running easy backfill. If that's the top level way that we've configured the scheduler, when a user requests 64 nodes and starts a shell script under those nodes, they get their own scheduler and their own set of those modules that I just mentioned in the previous slide that are scoped to their user. So as they subdivide these resources within a batch job, they can actually change the match policy and the queue policy to be more targeted to their workflow. You can keep doing this infinitely. So there were 64 nodes in the previous slide. Now, if you imagine you 16 times started another level of scripting and started another batch job, you could do a first come, first serve queue policy where you're just churning through jobs as quickly as you don't worry about backfill, you're just churning through jobs quickly. And this is a node exclusive. You can change the policy to be node exclusive, or more commonly, we would have a node exclusive policy at the top level, and you would change that to be non-node exclusive within a user's application. But because of the subdivision of resources, by the time you get to the point where you're running on just one node or just a smaller subset of nodes, you can run as many jobs as you want, and they're not hitting the top level of scheduling. They're opaque to the level 0 of the system instance. So this enables something that Nate mentioned in a previous slide, and it was kind of the reason that users were running Flux under Slurm or LSF for a while. It enables you to just hammer the instance with a number of small MPI jobs and not worry about the bottleneck that could create if you were doing that through, say, srun, where the job sets were running through a kind of shared daemon. The recursive model is kind of one of the above all Flux design principles. So it's something that we end up thinking about a lot when we're developing plugins or we're developing external services. Is okay, how is this going to work when a user starts a subinstance? And that sort of separation of concerns means that some of the features that are enabled by, say, having there's an elevated privilege bit prologue of a call to srun that you can add elevated privilege features to the beginning of a MPI run in Slurm. We can't quite enable that in Flux because we're always thinking about, okay, well, a user's going to be running MPI jobs that are going to be that are never going to hit the system instance. They're always going to be completely scoped to their user. So that's what I mean by saying like calls up to the system. It calls up to privileges that the system instance had from a user instance are not something that we support. Another thing that we are always thinking about when we're developing these plugins is portability. So how can we make sure that we can run across any Linux distribution? Maybe a year or two ago, I think that Vanessa Socket and Jim Garlick spent like 4 hours in an afternoon getting all of the glibc dependencies out of Flux core. So now there's an Alpine container that we test all the time. So Flux can run under Alpine Linux. Keeping all the hardware specific and fabric specific code and plugins is another thing that we try to do. We try to keep the core set of Flux services lean so that there's more iteration on the plugins, and it allows people to compose an instance based on only what they need. And then we try again to minimize as much as possible the elevated privilege calls that we're making. So all of our set UID helpers for multi-user instances are kept in a separate repository, Flux Security, and that makes sure that there's less iteration on that repository. All of our security code gets appropriate scrutiny, and by separating that out, it enables us to have the user instance just working. So Nick, you've already talked about this a little bit, but you want to talk some more about running under running all over the place?
Yeah, one of the coolest things about Flux actually, and this is, just one of the, I guess, both features, but I guess initially it was a side effect of the design, is that due to the principles that Hobbs has just mentioned, principle of least privilege and the ability to run in a hierarchical manner, it's actually quite straightforward to get Flux working inside of a container. And not only inside of a container, but we also do support, things like Flux operator and have, tie-ins with Kubernetes if that's a direction you want to go in that is under active research and development here at Lawrence Livermore. But as we previously mentioned, you can run Flux under another resource manager, and you can run in containers. And because of that, we actually provide a variety of different containers that could fit a variety of different needs for testing various aspects of the Flux scheduler and how you would plug it into your applications. And so these containers actually just so happen to make some really great HPC base container images if you want to test out just whether or not your benchmarks even just build. They usually include a working MPI implementation and everything that you would need to test simple MPI applications with Flux. And we're trying to make progress towards making these containers a little bit even more focused on integrating with a variety of different vendors and other people who want to run Flux at their site so that you can test drive Flux before committing to installing it on an actual cluster. And so everybody here is actually just a few commands away from being able to run Flux right now on your local Linux laptop or desktop, and we're making progress towards deploying on Mac OS, and then pretty much you can run anywhere within a container. So this is one of the particularly exciting aspects about the Flux resource manager and where you can run it.
So some of you who've developed for resource managers might be familiar with Spank plugins. Actually, so my mentor, Mark Grondona, who's the Flux technical lead, was one of the original authors of this interface for Slurm. By no means so we have an interface in Flux called command line plugins, and by no means is that our only plugin interface. But we thought it might be interesting to kind of compare and contrast for people who've written Spank plugins in the past what is additionally enabled by the Flux plugin interfaces. So Spank plugins are there's a manual page that defines a bunch of C functions that they can call out to and that they're expected to implement. I don't know how common this is, but at least at our site we have a C Spank plugin that creates a bridge that allows you to write Spank plugins in Lua. So there are some Lua wrappers for this interface. And what a Spank plugin basically allows you to extend the Slurm command line for srun or salloc or sbatch with an additional long option. Most people use this to enable some sort of extra functionality. So I wrote one for one of our development clusters at LC that will mount an ephemeral ext4 block as a loopback device for a user that wants to do some kind of development effort that's larger than the amount of memory they have on their system. So you can use these to activate additional functionality in the job, and often they're connected to an elevated privilege prologue or epilogue that's enabling some feature. We have a CLI we have the ability to expand the command line in Flux for our allocation and job launch commands, but the string parsing is a little bit nicer because these plugins are in Python. So when you allocate resources or when you start a job in Flux, our commands are in Python, and they're taking the arguments that you're putting on the command line and turning them into a JSON, what we call a job spec, a job specification. That job spec becomes a message that gets sent up the overlay network. So by just sort of natively, we support JSON as an option for customization. Like Spank plugins, Flux CLI plugins are often connected to some prologue or epilogue that can say reconfigure hardware. So on El Capitan, we have the AMD APUs that can be split into 4 or 8 or 12 GPUs, and you get a commensurately lower number of cores on them as you do that. That requires an elevated privilege call, but is enabled by a user using a long option on the command line to do that. We also allow, so we've sort of separated what Slurm considers to be prologues functionality into 2 different options in Flux. So we offer prologues, but we also offer shell plugins, and a shell plugin is scoped to the user's shell. So when Flux finally gets its resources and launches a shell, we have a number of plugins that run either in C or Lua that will activate specific functionality that's scoped to that user's shell. It might be clear to you by now, but I'll just reiterate, because this is something that kind of trips people up as being a little different from other resource managers. We don't have a concept of job steps in Flux. We just have jobs. So an srun in Slurm is considered a job step, or I think it's I can't remember what the LSF command is. In Flux, we just have jobs. So a Flux run at the top level, or a Flux instance, or a Flux run under a Flux instance are all equally jobs. So they all spawn the Flux shell. The difference between Flux run and Flux alloc is a little different because you're getting a sub-instance and all of the modules with that. But yeah, this means one of our focus areas is being able to sort of present the jobs that are running in a sub-instance more natively to, say, system administrators. Yeah, and then user sub-instances don't have access to services that require elevated privilege, obviously. Like a sub-instance that's scoped to the user can't have a prologue before all of its jobs that's running its root. That wouldn't be safe. We're kind of going back to the part where I know that everybody who runs on an HPC cluster every day knows these things, but in the interest of explaining how our users run on our clusters, they run through the command line. They have scripts with submission directives in them. With Flux, we also offer a Python API. So I'll explain a little bit about that in a minute. But the Python API, submitting a script with submission directives or submitting jobs on the command line, all create like equal citizen jobs. So a Python submitted job is no different looks no different in our to Flux than a job submitted through a script. And in the middle of this arrow between a user submitting a script or scripting with Python and getting out whatever simulation whatever scientific answer they're looking for is a state machine. So this is documented in a request for comments on the Flux website. It's RFC 21 job states and events. And this state machine, every job moves through this state machine in some way. When jobs are new, they get validated, they get evaluated for dependencies, they get a priority assigned to them if you're running multi-user via the accounting plugin. And one of the unique things about the state diagram is we have another plugin interface called JobTap plugins that allow you to attach a callback to each of these states. So you can register a set of things that needs to happen at each of these states with the job manager for jobs. Inside this box, a job is considered active. So this is so for the entirety of the state diagram, a log of events is kept, but within this box, a job is considered to be an active job. These are, and then when it gets out of there, it's an inactive job. Jobs at the system instance level and in subinstances all go through the state diagram. So you can imagine that while a subinstance job is active, it's spawning other jobs that might be, eventually ending and be inactive. It has some number of active and inactive jobs within it. In addition to the callbacks that we offer so right at this point, before and after a job runs, we have that prologue and epilogue that people who've developed for resource managers before are all too familiar with. And we also, right before a job runs and its shell is started, when its shell is started, we have that set of shell plugins that I mentioned. Because we're in a libfabrics environment, I'll show one example use case where Jim Garlick had to pull a lot of the different plugin interfaces together to support the Cray VNIs on LCAP. So the VNIs are a way of partitioning off the network partitioning off the network on LCAP for a user. I think it's called the Virtual Network Interface. Nate can correct me if I got that acronym wrong. But when a job is submitted, it requests a VNI. And when it gets to the sched state, there are, I think, 64,000 available VNI tags available, which is just an integer. A JobTap plugin is keeping a record of the integers that it's issued and the integers that it can still issue, and it has a round robin allocation for this. It can tag the job with a VNI. So the JobTap plugins that I mentioned and a lot of our other plugin interfaces can add metadata to the job spec as it's going through these states. That gets pulled down when the prologue comes into play and a CXI service gets started. So that's the piece that actually partitions off the network for the user's job. Then it's shut down via the epilogue, and the tag that it was assigned, that integer, is released back into the pool of tags that the JobTap plugin can continue issuing to other users. Nate,
Flux,
do you want to?
Yeah, Flux is available, as mentioned before, in a lot of different places. It's an open source project, so you can always obtain the source code off of GitHub. As mentioned previously, we already have containers. One of the perhaps more robust ways of installing it in production would be to use the SRPMs and install it that way. However, we are currently working on packaging. It is on our roadmap to have debs and RPMs available for a variety of instances and channel repos, so that it would be even easier to install Flux in a robust fashion, keep it up to date. And then Flux can also be installed via SPAC, or the Supercomputing Package Manager, which was also developed here at Livermore and is also open source. And a little bit more like a Nix or Geeks style way of installation, where you would be building it from source in a very controlled environment, or you can also just do the make install thing and build it from source on your own. Next slide, please. So getting started with Flux, the commands and interfaces, we previously, briefly mentioned the batch script directives. These are very similar to a variety of other schedulers. All you really need is Flux, uppercase or lowercase is fine, with a colon at the beginning of your job, of course, commented out with the hashtag. And so you can specify whatever you need to that way. But before you do any of that, if you are starting Flux from cold and dark on a system that does not yet have the broker 0 running, you would have to do Flux start. Or of course, if you're running under another scheduler like Slurm or LSF, you would also need to do Flux start at the beginning of your job so that you get into broker 0 environment. And then, of course, as previously mentioned, you can just use Flux run to go ahead and execute what would look like a job step, but essentially is actually a job that's running out on your allocation. And then you can also see running jobs with commands like Flux jobs. And there's also a variety of other commands we have documented, like Flux resource list to see resources and things of that nature. Next slide, please.
So I pushed up, and I'll start it in a minute, a very small container demo that's based on our Flux Sched container image. I'll leave it up after this talk so people can pull it down. It's exactly the Flux Sched bookworm Debian container image with just a couple of scripts that I pulled from my work in there. It'll be frozen, so I won't keep it up to date, but you can always go to the FluxRM Docker Hub repository for our official container images. So I'll just run this container really quickly. Well, actually, hang on. I'll show you how I built this container first. So this is exactly, like I said, it's exactly our Flux Sched container with a couple of extra scripts and some demo things. And I made the entry point of the container Flux start. So I made it Flux start with this small test instance flag. The test instance flag just is a flag that we developers commonly use to, when I start this instance, what it will do is it will make it look like I have 4 nodes. And how it does that is it starts a broker tree of 4 brokers and just treats each as if it were a node. This is something that we use for testing all the time. I'm just on my laptop. I don't actually have 4 nodes, but it's something that we use for testing all the time. I have all of the modules loaded that I would normally have on a system instance, and including the Fluxion scheduler. So if I submit a bunch of jobs, and I'll just submit copies of all of the same job, and then I look into Flux top, I get a picture of how the instance is churning through all of these jobs. You can imagine if you were to run that same command on like Tuolumne or El Capitan, you'd see a ton of churn and be able to see who's using the system the hardest in any one moment. Within our containers, as Nate pointed out, you can kind of treat them as a view into how a user of HPC would be interacting with an HPC cluster. So if I compile some MPI code, I can just run normal MPI code in my container. And one of the things that we run at LC that's a little bit it's available to all centers, but it's a little bit unique to LC as MPI bind, which Nate and Edgar Leon have developed with others. If I can actually MPI bind, when it's registered as a plugin to Slurm, has to run as a prologue. But in Flux, I can actually build and install MPI bind as a shell plugin and run it under my user ID. So if I
just as some background, MPI bind is essentially our affinity setting tool that uses NumaCTL to very thoroughly restrict running processes and tie them to exact cores and resources within a node. So to make sure that you get exactly the locality that you thought you were getting. And the reason we, developed MPI bind is because we were getting lots of unexpected affinity behavior, and we wanted a way to make absolutely sure we're getting exactly the process affinities that we thought.
Thank you. Yes, I totally should have explained what MPI bind was, but if I add this to my if I take the MPI bind plugin after it's built and add it to my shell path, so this is just an environment variable that's searching for, and I have to make sure I spelled everything right. That's searching for shell plugins. Now, when I run if I run any MPI job, and I can get MPI bind to print the mapping that it's going to use of cores to MPI tasks. And this is a little bit more clear if I use an MPI code that actually shows that I'm being honest, and you can match these virtual CPUs up with the tasks they're running on. I mentioned that you can run jobs through Python. There's an example of that in this container too. So let's see, it's called the example script. This script is taking an argument on the command line of a binary that you want to run and running it 100 times using the Flux executor. The Flux executor was developed by one of my colleagues, James Corbett, who based it on the concurrent futures executor. So those of you who are Python nerds will recognize that as a kind of that was the inspiration for this. It's just whereas the concurrent futures executor is treating, I think, processes and creating processes and giving you a callback it's taking Python callables and giving you a future. This is taking Flux jobs and giving you a future back. So if I submit this example script with just in true, you can see it churn through all of those jobs. You can it averaged 448 jobs a second. So the Flux executor submits jobs is probably the quickest interface we have for submitting, let's say, uniform or even non-uniform jobs. The last thing that I'll show you in here is if I were to allocate a node out of these 4 nodes that I have, then I get a whole new, as I've mentioned before, I get a whole new scheduler in this sub-allocation. But I can also reload that. I can either load that scheduler with some configuration options that will change the scheduling policy, or I can reload the scheduler with a new scheduling policy. So I'll show you reloading the scheduler. This script just has some extra configuration in it for the scheduler. And now if I look in, when I loaded the scheduler for the first time, I just got default options. If I look in our logs now, I can see that the scheduler loaded with a hybrid backfill policy and a couple of other different parameters. And I think that's about all we wanted to show you in the container demo. Nate, was there anything else you wanted to?
No, I think that's pretty much it. Yeah, feel free to download this container image and play around. We have it available in both AMD 64 and for Apple Silicon and any ARM64 architecture. So yeah, just definitely feel free to poke around for yourself and see what you can do with it. Like I'd mentioned before, it has a channel repo installed, mpitch available, and Flux, and so you can build benchmarks and see how fast your memory is, and right on your own system. So that's totally ready for you to start playing with.
Yeah, that's a good point. All of our containers, or most of our containers, are Docker manifests. So if you pull it down on any like MacBook or x86 laptop, it'll automatically pick the right platform architecture. as Nate lived through and I got to watch, the acceptance of El Capitan brought together an enormous amount of effort from the system software developers of Flux, the our partners and among the vendors, and users using Flux in anger for some of which for the first time ever, as we were trying to get El Capitan available to users. So a Flux instance of nearly any size is possible and stable, but there's still work to be done in many features that a lot of users want to see in a resource manager. So several important features, and there's a longer list of things that we're working on in 2026 available in the Flux Administrator's Guide on our website. But just a couple of things that we expect progress to be made on in 2026 are rolling software upgrades. So being able to have brokers right now within the Flux broker tree, it's assumed that all the brokers are running the same version of Flux. We'd like to be able to have a broker from like a previous version connect to a newer version so that you can roll an update across a cluster. Restarting with running jobs is another big one. We need the ability to be able to. This is actually a little bit more nuanced, because if you think of that broker tree again, what happens is if a broker dies, its children automatically get sig kill, because we can't sort of track their work without their parent reporting that up the broker tree. We'd like to be able to restart those brokers, which are already wired up to systemd. So the first part of that is kind of done. But reservation support is another one that we're working on. I was just talking with Mark Grondona about this on Monday. This is not only supporting a specified start time in the scheduler. We're also sort of thinking through how we want to present this to users. So, there have been one of the early use cases for Flux was having a multi-user subinstance. So starting a subinstance of Flux underneath a system instance that also sort of behaved like a system instance that would allow multiple users to connect to it. And then, as Nate mentioned, package availability. So we have source RPMs that are on GitHub with each tagged release, but being able to just go DNF install Flux core and have it just work is not something that the team supports currently. We have a very generous volunteer at Red Hat who's working on. He's a Red Hat employee. His name is Kushan Gupta, who's working on getting us into the Red Hat extensions repository. I hadn't heard of this. It's kind of a newer thing, but it's different from EPEL. So I can point people at the RPMs that he's working on if there's interest in that. With just our last couple minutes before, I want to make sure we leave the full 15 for questions. These slides will be available. These are different ways to contact us. We're a very GitHub-driven team, so if you open GitHub issues for questions or bugs, that's pretty much the quickest way to get in touch with us. And finally, I wanted to make a plug we're having, for the first time ever on March 17th, as part of the High Performance Software Foundation conference in Chicago. We're in the process of joining the High Performance Software Foundation. We're having a Flux, I think we're calling it a community meeting. And we're asking the Flux community to come join us for an afternoon of talks about Flux. Last year, all of the HPSF talks were recorded, so I imagine that these will also be recorded and available free to view online. But Vanessa Sockett has done a wonderful job putting together an agenda of different developers from Lawrence Livermore. We have a couple of students from the University of Tennessee that will talk about some of their work, and we'll just have an afternoon of lots of time for questions and lots of ability to interact with Flux developers. And I think that we hit the nail on the head. We're right at 10:45.
Yeah, and I just want to add one more thing. So the HPSF is the High Performance Software Foundation, as Hobbs had mentioned. Flux is committed not only to being an open source project, but is also now open governance with it joining the HPSF, which means that when you contribute to Flux, you can do so without worrying about contributing to something that is, specifically governed by or tied to a particular institution or organization. So by being tied with HPSF, we've gone through all of the process with the Linux Foundation. It is a Linux Foundation project that allows us to make sure that we support a variety of different contributors from a variety of different backgrounds.
Yeah, there's a lot to be excited about with the Linux Foundation. One thing that I know that Jim Garlick has been excited about is I don't know how soon this will happen, but there's like the Linux Foundation specifies. The Linux Foundation has a really robust set of training resources. And so there's like the potential for us to become part of that as we, formally join and get involved in that. So with that, I'll shut up. Thank you, Nate, and ask if there are any questions.
Thank you, Hobbs and Nate. So we have a couple questions that I received in the chat. As I read these out, if anybody else has other questions, please feel free to pop it into the chat and we will get to it as well. So first up, do you have a list of granular node scheduling policies on the Flux documentation sites?
Yes, although one thing we're working on with the Flux documentation is so the framework projects, because they all have an individual read the docs, the top level search doesn't get all of them. There is a list of scheduling policies. It is I will pop this into the chat. It's in the Flux scheduler documentation. I'm gonna stop sharing my screen and I will pop the link to it in the chat as the answer.
Great. Okay, and then we had another question submitted. How hard is it to write a scheduler plugin?
A scheduler plugin. So that can mean a couple of different things. Whoops, I'm trying to, let me copy this link over real quick. That can mean a couple of different things. The scheduler itself is a plugin. So the scheduler avails itself of the Flux, the scheduler is a Flux broker module, the Fluxion scheduler is. And there is a simple scheduler in the core tree called sched simple that's just a first in, first out. It doesn't understand GPUs. It's just a very, I'm trying to find a nicer word to say than dumb, but it's a simple scheduler. Oh, sorry, go ahead.
Oh, one more point to add, I guess, to that question, if this is helpful. The question is regarding interacting with the job queue.
Interacting with the job queue.
But continue.
Okay. If you want to completely rewrite the scheduler altogether, which maybe somebody does, the protocol between Flux Core and Flux Sched is documented in what's called an RFC, a request for comments. And on the last slide of this presentation that'll be posted, there's a link to RFC number 13, which is the simple PMI RFC. If you can get to that one, you'll see in the sidebar, I think it's RFC 25, is the resource acquisition and allocation protocol. That's very nitty gritty. I have a feeling what this question is getting at is how easy is it to write a plugin that can influence scheduling decisions? And for that, I would kind of guide you more towards the policies that we already support, which are linked in the chat, or excuse me, the accounting plugin also has the ability to influence scheduling by assigning priorities to users. And the way that it does that is documented in the accounting documentation. It's a fair share algorithm. There's a
variety. Yeah, it's a very Flux is provides a variety of robust interfaces throughout the internal interface. So throughout the internal architecture of the project. So there are lots of places where you can plug in and do a lot of really interesting stuff with how you want to influence scheduling, multi-constraint, et cetera, via the variety of different interfaces. The thing we always guide people towards first, of course, is what you need to do possible in just a prologue epilogue. So it's always good to look at the prologue epilogue first about, okay, can I just do it there? And then, really look into, do I really need to start, actually interfacing with the core of the scheduler and figuring out how it's going to allocate resources.
Great. So it looks like our next question here in the chat is, does Flux have HA automatic failover support for rank 0 broker?
That is one of our focus areas for 2026.
Okay, wonderful. Okay, our next question here says, Flux presumably already runs the job ID service resource index stuff for Slingshot jobs. Has anyone started to see if or how this might be used for UEC?
I will kick that one to Nate because he is the most involved in the UEC.
Yeah, we've been interacting with the UEC project on this, and yeah, we do. We are very interested in how this could interface with UEC, and so we are currently tracking that in terms of how job IDs will be handled at the software layer. So yes, we're definitely tracking that. We're definitely working on it, and we're going to do our best to be UEC ready, UEC compliant as quickly as possible in terms of not just compliant being able to run it, but also being able to take advantage of a lot of the features. It's a great opportunity. These types of, one of the reasons we're here and one of the reasons we support, as you can kind of tell, we're really into kind of open governance here, right? So we're in the HPSF, SPAC is also in the HPSF with us. And we really like the opportunities that are provided by organizations like the Open Fabrics Alliance and the Ultra Ethernet Consortium in being able to allow us to interface in a more standardized way between Flux and a variety of different vendor hardware, saving from deduplicating effort from our side in terms of NRE or non-recurring engineering effort, but also from the side of the vendors, right? So it's a lot easier for us all to agree on some standard interfaces, and so we're very excited about UEC.
Perfect. Okay, and then we have one more question here. Where are the packages for RHEL and what engineer is working on this for those of us that might need to chat with them?
I am trying to post a link in the chat, and for some reason my cursor is not working. It is on GitHub under Kush Gupta Flux-RPM, and I'm trying to, hang on, I'm going to try reopening the chat and seeing if I can. There we go. Okay. It's linked in the chat.
Perfect. Thank you. Okay. Are there any other questions for Nate and Hobbs?
If whoever asked the scheduler question can tell, I'm worried I might have just confused you on that one. So I don't know who asked that question, but if you can chime in as to whether we answered that.
It came from Mike.
Oh, okay, cool.
I think we
Mike
were
knows,
good.
Mike knows how to get in touch with us.
Yes, yeah.
Yep. Well, we work with you already, so yeah, we'll for sure look into that.
Perfect. Okay, well, that brings us to the end of our question portion. So thank you everybody for joining us today. Thank you, Nate and Hobbs, for presenting. And this webinar will be available on demand on the OFA website, and it will be sent to folks who registered for the webinar and attended. So thank you all very much.
Take care, everybody.